today that the standard model of GRBs basically works, quite decently. And the standard model is what is used by the observers. It's always used by the observers because it's reasonably simple, well understood, so the calculations can be made so that you can compare the observations. And so that all looks very nice, but of course once you start getting more refined data, then you start finding out that the model, has some little problems. And so, in particular, Swift and Fermi have, brought a lot of new information, and so it has become necessary to figure out what is well established, or what is okay with the models, and what are the problems that one has to address. So the blast wave model, in principle, is that you have a central explosion and you're sending out shells of matter at relativistic velocities. They may have different Lorentz factors, and then eventually, the two shells, if gamma 1 is a bit larger than gamma 2, the two shells collide at some point, you have an internal shock. Further out, then you have the interstellar medium, and you start switching out the interstellar medium, then you have the external shock. So these are you get your internal shock, and so that's the picture. And then eventually you have the external shock, and you do the X-ray and the optical and the radio afterglow, etc. Now, for the afterglows, the synchrotron shock paradigm predicts a spectrum which, as I mentioned, is something like these. So the electrons are shock accelerated. There is a minimum electron random Lorentz factor that corresponds here to some gamma max. Random, not the log Lorentz factor, but the random gamma max. And so that corresponds to synchrotron peak frequency. Above that, there are power law electrons. So you have power law electrons extending from gamma mean to some gamma max. And that gives you this power law here. That's the cooling break. And the low energy asymptote is if you're plotting here flux as a function, so energy as a function of energy, then it's energy to the 1/3. And then there is self-absorption. And these characteristic frequencies during the afterglow, as the fireball decelerates, the Doppler factor gets lower and lower, so these characteristic frequencies move down in energy. And so comparing it to observations, one finds that, I haven't plotted here many data points, but there is only the first fit that was made, and many other fits have been made, and so these model fits quite recently. So for afterglows, the synchrotron shock model works well for practically all bursts. There are a few weird ones where you have something that is good to consider extra, but the basic model works pretty much well. Now, that's the afterglow. The afterglow is the longer wavelength, X-ray, optical, radio, etc. The front emission is where most of the energy is, it's the gamma rays. Okay? And so the spectra are broken power laws. Okay? And so in principle, so these in energy F nu. Okay? And so there is a low energy slope, which for pure synchrotron should be nu to the 1/3. And these should be electron index minus 1/2 if it's straight synchrotron. These in energy per energy, and these photon number per energy. Okay, so photon number per energy, the slope is roughly, so there is, you call these slope alpha and these slope beta, and it's fitted by the so-called band function, the alpha and into the beta. So you know that the break is that, above the break is that. And so the indices have a distribution. Alpha has a distribution, and beta has a distribution, and energy has a distribution. And so for pure synchrotron, these minus 2/3. Indeed, energy per energy is 1/3, then photon per energy is minus 2/3. And so the slope should be minus 2/3, so it should be somewhere here. Okay? Now there is a distribution, so it doesn't look like a single particle synchrotron spectrum. But of course, if you have a distribution of energy, so the gamma min, which comes here, if in a verse, you have a distribution of them, you could have some values that can accommodate that. Fermi also made a more detailed analysis of the distribution of these low energy spectral index. Okay, and so here is the minus 2/3, and you see their values below and above. Now, some of these values are a problem for the synchrotron interpretation. That's why they call it the line of death problem. And it's the fact that, so we do have a lot of indices which are flatter and indices that are steeper than the minus 2/3. So is this a problem or not? So what it should be is it should be in F nu, it should be 1/3 and something like, minus 1 or something. And in photon number n sub nu, it should be minus 2/3 and so on. Now if you observe a slope which is flatter than 1/3 or which is steeper than minus 2/3, that's not a problem because you can consider that these individual electron spectra are distributed, and so you can make a slope here which is flatter than 1/3 or steeper than minus 2/3. The problem is when you have values of alpha which are greater than minus 2/3 or which are steeper than 1/3. That is essentially impossible to cover with a distribution of gamma mins, because no matter how you arrange these guys here, you can never make them steeper than 1/3. So that is a problem, and it is a major problem of the synchrotron interpretation for the prompt emission. You don't find these in the afterglow, this problem, but you find it in the gamma ray prompt spectrum. An alternative possibility is that the emission spectrum is a combination of two types of radiation. One would be the radiation of the photosphere, which previously was largely neglected, plus maybe the internal shock synchrotron radiation. So the internal shocks might produce this thing here, and then the photospheric spectrum is, if you take it to be a black body, then in F nu, here you have an asymptote of nu squared. So you can make very steep spectra. And if there is Comptonization of the black body, then that can be shifted to higher energies. Okay? And so you can achieve, below the peak, you can achieve very steep spectra, which was the problem I mentioned before. And if nu to the 2 is too steep, it's not a problem. You can have, a combination of temperatures, and so you can always flatten that spectrum as much as you want. So, all you need is that the peak be near MEVs, and so if you put in numbers for the photospheric radiation, then you can do that. So you can work that. You can resolve it, but you have to invoke that the photosphere plays an important role, maybe a dominant role in the prompt emission. So there has been a paradigm shift, and it is over the last 10 years, essentially, or maybe even 12 years. The old paradigm was that, you had internal shocks producing the prompt gamma ray emission and the external shock producing the long-term X-ray optical radio afterglow, and that the photosphere was weak. It had essentially the wrong spectrum. We thought was thermal, we didn't see thermal spectra, etc. Internal shocks, on the other hand, are very good at explaining the quick variability, the fast variability, time variability of the spectrum, the light curve having a lot of peaks. You can calculate it easily, it's easy to model. It did have always the problem that its radiative efficiency is relatively poor. So you had to, put up with efficiencies less than 10%, sometimes it was 5%, and that could produce a problem with the energy budget. With the external shock, there was never a problem. That always worked for the synchrotron interpretation. But these issues that the spectrum internal shock is wrong and that the radiative efficiency is poor, that needed to be addressed. And so the new paradigm is that you have the photosphere, and that the photosphere is actually strong, especially if it's a dissipative photosphere. It's a photosphere where you have either shocks occurring in the photosphere or you have magnetic dissipation. Then previously it was thought that the photosphere was weak because there was no dissipation in it. But if there is dissipation, then you get good radiative efficiency. And so to emphasize more the photosphere, you have to argue that the internal shocks are weak. Of course, the radiative efficiency always was weak, but you can make them even weaker if you argue that maybe magnetic fields are important, then the Alfvén speed is large, and the relative velocities are always low. And so you can have the photosphere being strong and the external shock being strong. So there have been models in the past 5 years that have explored these avenues. So the score sheet then is for the afterglow. The standard model of the external shock, forward shock and reverse shock, is fine. It works very well. Minimal reasonable extension addresses practically all issues. Chrome gamma rays have these two vexing problems. One, the low radiative efficiency for the internal shocks, and the fact that you have the wrong spectrum. You're in the fast cooling regime, and so you have to do something about the spectrum. One problem is if you have distributed heating, then you can sort of address that. All right, so let's de-emphasize the internal shocks, and it's one way to solving the problem, de-emphasize the internal shocks and replace them with the dissipative photospheres. Or we consider the internal shocks, but we have to modify them. We have to introduce slow heating, let's say turbulence behind the shocks, and argue that you have second order Fermi acceleration as opposed to first order, or in addition to first order. Or that we have magnetic dissipation, which increases the radiative efficiency, or that we have hadronic cascades, which naturally provides a slower sort of input of energy into the shock, and that sort of solves the spectral issue. So there is the old paradigm, internal shock, external shock. There is the new paradigm, photosphere, external shock. Now, how do we deal with these photospheres, and how do they touch in other aspects? So you remember that I mentioned that there are these two interesting phenomenological relations. The spectrum being proportional to the ISO to the 1/2, or EP being proportional to the jet energy to the 0.7. These relations are called the Amati relation and the Yolanda relation. So what are the physical reasons that could explain these? So in internal shocks, you can more or less explain it, the Amati relation, because the EP is the synchrotron peak frequency, and the synchrotron peak frequency is proportional to the observer frame. It's proportional to the Bulk-Lorentz factor to get to the rest frame of the gas, and then in the rest frame of the gas it's proportional to the magnetic field strength, or moving magnetic field strength, and the random electron Lorentz factor squared. The random electron Lorentz factor squared in internal shocks is more or less a fixed quantity, so it's only gamma beta prime in the observer frame, and that's just the magnetic field as seen in the observer frame. And that, if that is in some kind of equipartition of energy, then it's proportional to the internal energy of the gas, the photon energy, to the 1/2. And in the internal shock model, you can figure out that that's luminosity over r squared to the 1/2. And so eventually you get that your EP goes as L to the 1/2, and the radius is proportional to T variability times gamma squared. If these two factors were constant, then we would have EP is proportional to the L to the 1/2. The problem is that the variability time scale and the Bulk-Lorentz factor differs, and it can change, so there is no guarantee that these factors is constant. So, you know, you have a sort of an explanation, but it's not very satisfactory. Now, in the photospheric model, you are talking of the peak being roughly given by the temperature of some kind of a black body, even if it's a distorted black body. So the observer frame EP is the Bulk-Lorentz factor times the co-moving temperature. And the co-moving temperature is just given by, you know, it's luminosity over gamma squared to get to the observer frame times the radius. And it just comes from saying that that the luminosity is r squared sigma t to the 4th. Okay, that's why you have the 1/4 here. And so that's gamma squared L to the -1/4, because the photospheric radius goes as L over gamma cubed. And then, if you correct for the jet beaming, then typically the luminosity goes as the angle of the jet to the -2 causality. And so you would get that it's L to the EP goes as L to the 3/4. So that again is not good. In fact, you have some relationship, but it's not the right one. But if you argue that the photosphere occurs at a set radius, a fixed radius, not a radius that varies, but a radius, let's say, which is the radius of the progenitor, the Wolf-Rayleigh star, then D is a fixed number, and you get these, then EP is gamma to the 1/2, L to the 1/4. And in these model where the photosphere is at the radius of the star, then the Bulk-Lorentz factor is proportional there to theta to the -1. Theta is L to the 1/2, so you get your relationship, your relationship. So there is physics you can put behind, and you know it's more or less reasonable. Now, what is this business about a dissipative photosphere? So if you have an outflow. Then as the Bulk-Lorentz factor increases, so you have that when you reach when the Bulk-Lorentz factor reaches its saturation value, it reaches its terminal values, the gamma Lorentz factor goes up and then it becomes constant. Then the photosphere is out here, you know, it means that the sort of the radiation energy or the thermal energy starts to, it's adiabatically cools. And so the further out the photosphere is, the cooler it will appear. So if the photosphere is here, it will be, its temperature would be down, and if it's here, its temperature would be even further down. But if at some radius you have dissipation, let's say you have shocks near the photosphere, you have magnetic dissipation, then you reheat the photosphere. So you can get these higher temperature, and that can get your effective peak of the black body near the half-nanometer MEP value. So these are the dissipative photospheres. You get an effective photosphere luminosity and an effective photosphere temperature, which is higher. Now, where the photosphere occurs depends on the dynamics of the expansion. So normally we consider that for a long time we consider that the dynamics is dominated by radiation and that the inertia is provided by the baryons. And then the Bulk-Lorentz factor grows initially with radius linearly, and then then the baryons then on, there is no more internal energy to put into bulk energy, and from then on, the bulk Lorentz factor is just constant. And the photosphere typically occurs here in these regimes where the Lorentz factor is coasting. On the other hand, so that's at a given radius. On the other hand, if the internal energy of the jet is largely dominated by magnetic stresses, by magnetic fields, not by the radiation, and the inertia is still given by the baryons, then you can show that reconnection causes the bulk Lorentz factor to grow much more slowly. It grows as radius to the 1/3. The saturation radius occurs much further out, so the coasting regime occurs much further out. And actually, a photosphere occurs here in this growing part of the curve. So there is a different Lorentz factor for the photosphere, and it also occurs at a different radius from the central engine. So let me not go into details, but you can calculate the photospheric radius by saying that the scattering optical depth, which you can express the moving scattering optical depth, which you express in the piece, has to be set equal to unity, and that gives you what is the radius at which the photosphere occurs. And so, depending on how the Lorentz factor grows, whether it grows as R or grows R to the 1/3, then tells you, that the photospheric radius depends on the saturation gamma like these or like that. So you get two types of cases. Is the baryonic photosphere radius and is the magnetic photosphere radius. So that's all fine, and so to make this thing work, we need the photosphere to be dissipative, to have dissipation near the photosphere, and there are various possibilities for that. One of them is that there are magnetic fields, and you get reconnection of the magnetic fields, and when you get magnetic reconnection, you can accelerate electrons and positrons, and photons, etc. You will accelerate also protons if they are present. Alternatively, you might have shocks which occur everywhere, including at the photosphere. So if they occur at or below the photosphere, you will have dissipation too. So it will give you more or less the same result as that. An additional source of dissipation is if you consider that the outflow has not only protons but neutrons. I mean, it should have neutrons because that's the normal stellar material. It's more or less equal number of protons and neutrons, just as in nature. Especially since we're talking of mainly hydrogen and helium, those are the most abundant elements. So they have, hydrogen is of course protons, but near the core of collapsing stars, mainly heavy elements, and the heavy elements, they have more or less the same number of protons and neutrons. So those can have nuclear collisions, and those will be relativistic electrons. Okay, so some examples of dissipative photosphere calculations. These are calculations by Asaf and colleagues. Look like these. So these are Monte Carlo simulations. One of them is one where you have slow dissipation and shock dissipation, and either that or that, and you include synchrotron radiation, Compton, inverse Compton scattering, pair formation and annihilation, etc. And so you get spectra which have a, you can have a steep low energy slope, and then you can have high energy slopes which don't look too different from the observed values, depending on where the dissipation occurs. If it occurs at optical depth unity, or if it occurs at higher optical depths. So you can get photospheric spectra that look fairly reasonable. Now, in the case of the magnetized dynamics, as I mentioned, the expansion is different, so gamma goes out to the 1/3. And if you have a dissipation, then you can get the parabolic spectrum. Things whether you get internal shocks or not depends on whether the magnetization parameter drops to a low value after you exit the photosphere. And if that's the case, then you can have internal shocks, which might produce additional radiation, but if the magnetization remains high outside, then you sort of suppress the internal shocks. You would only have the photospheric component. And the external shocks might look the same, except if the magnetization is high, then that might suppress the reverse shock. That might be a good thing because the prompt optical flash is generally ascribed to the reverse shock, and so it's not observed in the majority of bursts, it's observed only in a minority of bursts. So one might suspect that in fact the magnetization parameter is high, and therefore in most cases you don't have a reverse shock, and also you don't have the internal shocks. So these are a typical calculation of a photospheric radiation producing the prompt LED spectrum, and then it gets upscattered in the external shock, which has a forward shock component and a reverse shock component. So you can have the external inverse quantum component, so you upscatter these photons both by the forward shock and by the reverse shock. And you can get spectral fits either to Fermi bursts, Fermi-like bursts, which, you know, more or less agree. But you can get the same type of goodness of fit for either a photosphere which is magnetically dominated or for a photosphere which is baryonically dominated. So adjusting parameters, you cannot tell which of the two dynamics is the correct one, whether it's magnetic dynamics or baryonic dynamics. So you get good fits, and you can. One of the good things is that you can actually, adjusting parameters, you can also make sometimes a single band function fit without a second component, or you can adjust them some other way and you get a second component. So the fits are there, but there are enough parameters that you can play around, and on the one hand you can explain many things, on the other hand you're not exactly sure whether it's the right thing or not. So they're not unique. Let me discuss the other way of having dissipation in a photosphere. So you have protons and neutrons in the outflow. And initially the protons and the neutrons are coupled by nuclear elastic collisions. Right? The radiation and the magnetic field pushes the protons because they are charged. The neutrons are neutral, they're not pushed by either magnetic field or radiation, but they're coupled elastically to the protons by just elastic nuclear collisions. But at some point, the collision time becomes longer than the dynamic time, and so when the collision time becomes longer than the expansion time, then the neutrons start to lag behind the protons. The protons are still pushed by the radiation of the magnetic field. The neutrons are not. And so there is a relative drift velocity between neutrons and protons. And when this drift velocity exceeds half the speed of light, the collisions, the nuclear collisions, become inelastic. When they become inelastic, then you produce pions. And then the pions decay into neutrinos and relativistic positrons. And the relativistic positrons, essentially, they have a lot of energy which they deposit in the gas. They can interact with the other sort of thermal electrons, and they reheat them, so you get dissipation. In addition, you get some 30-40 GeV neutrinos, which are interesting, and also some high-energy gamma rays. So this has been exploited by Andrei Belogorodov in a very nice calculation. So he considers these proton-neutron collisions below the photosphere, and that causes a rather strong heating of the photosphere. So it's a strong dissipation by these inelastic collisions. So it's a very effective dissipation, and you can get some greater than 50%